Hello everyone, welcome to today's class. So today we will be talking about language vision models and bias in these models. So you might be kind of wondering why there is a slightly different format to the way how we are presenting the slides now. I decided to kind of make it more public because I think these topics are kind of interesting and important, and there is not so much material out there that would discuss it. There are some information, of course, in like papers and stuff, but nothing collected into one kind of a lecture. So yeah, that's why you are looking at this in this way now. So let's look at the overview of what we will be covering today. So we will start with some sort of like background concepts that will help you understand what we will be talking about today, and that will be the text to image generation. We will introduce the clip model, which is at the base of all of these techniques. We will show how this model can be used for text-to-image generation. And then lastly, we will look at some examples of bias in these language vision models. We will also look at some examples in the artworks that use these models, and that's it basically for the pre-recorded lecture. And later in the live session, which will be more standardized, we will be looking at one of the text-to-image notebooks and playing around with that. Okay, so let's start with the motivation. Why do we even care about this topic? So I think the whole overall kind of idea is that we want to have some sort of machines that understands us. So this is the sci-fi promise of like speaking to an AI, and the AI kind of can get what we mean, even if the commands are not super clear, even if there are some ambiguous sentences. So there is a comic from XKCD with Captain Picard asking the replicator for the tea. So he always says tea, Earl Grey, and then an adjective, and then basically going from hot all the way to different possible adjectives you can see. So tea, Earl Grey loud, or tea, Earl Grey, tea for him too, which is kind of just sort of showing that human language is kind of like quite ambiguous sometimes. So it's interesting to kind of work in this area. One example of what we would like to kind of achieve is that we already talked about having generative models that can like generate images from some domain that we train it on. But sometimes our control over these models is quite limited. So what we would like to have in some cases is some sort of a guidance mechanism. So for example, being able to say to a pre-trained StyleGAN2 network, which is just generating faces, trained on the FFHQ dataset, basically a standard released model that we could download from the repository, and then tell it something like that we want an image of a man resembling a vampire with a face of Count Dracula. So it would start somewhere and then go in that direction to generate that image, and this is quite cool. Similar kind of motivation is that finally with these models we are able to generate really high fidelity images, really high quality kind of resolution and stuff. So if you remember in the previous classes, we were talking about models like Pix2Pix and CycleGAN, and often what we could train in the class was quite limited, and so the models had kind of low resolution, or we needed to use some tricks like super resolution to look at them, even to have them somewhat all right. But now this technique that we are talking about today is really like something else. The results of these are really really good. So like high resolution, high quality, high amount of detail, and there are kind of some tricks from the users using this, some sort of how-to instructions to really like play around with these models and to have them do something interesting in some way. And all of this is basically for free on the collab. So that's the kind of promise that we can just play around with these for free. All right. One other kind of interesting property of these models is that we can select the starting image, the seed where we are kind of going from. And so in this case, it's kind of like starting with a leaf-like structure and then generating into a city. And so, yeah, I mean, it's really useful to like mix concepts together, and maybe it's easier than what we would need to do in the previous models. So like training something like this would be sort of impossible with like guns and stuff, because you would have to have samples of each and then trying to find the interpolation there. It would be quite hard, but this technique actually can do this. And then finally, this is a really new and active field. So this is like relatively, well, let's say like 1 year old technique, and we can see new releases and new versions of notebooks that use these almost like quite regularly. And so, for example, the disco diffusion notebook, which we will also be using in the class, of version 5 has been released only like 1 week ago, so just a couple of days ago. And it's basically working the same way as the previous versions, but it's adding some tricks and kind of cool mechanisms how to like generate 3D like videos. And so also to just demonstrate that this is an active field, you can kind of see the first sort of results from these were from Clip plus VQGAN, and basically they were 1 year ago. And then these posts, or this post is by it is basically recent. It's from a few days ago, and it's kind of comparing the quality of these versus quality of these. And we kind of what improved was is on one hand the models that we are using, but also kind of the way how we are capable of asking this model to generate images. So being able to prompt with some specific keywords, for example. And so we will talk about all of this today, but this is just to kind of show that this field is really interesting. It can produce really nice images, and yeah, it's useful to kind of talk about. But there are also some problems with this field, and so we will get to that in today's class as well. Okay, so let's talk about the background of these methods. So the text to image. We kind of talked about these domain-to-domain translation models, and this meant for us in the previous classes image-to-image translations. So we had like images from one class, one domain, let's say, and then images for another domain, let's say night images and then day images. And you needed, or you wanted for the task that you care about, to learn this translation between these two. And I mean, the reasonable question here to ask is to just say, okay, isn't this just a domain-to-domain model? Can we not have a language encoder and an image generator and just plug them together? Well, the problem is that this is a really ambiguous task. As I was saying, that the language is quite like tricky sometimes. Even for humans, it's sometimes difficult to understand what other people mean, right? And so this is never like an easy way how to take something, encode it and decode it, like the interpretation is never one-to-one. It's also ambiguous because, like more people say, can have multiple meanings and can have multiple results. And so similarly, like with the models we talked about in previous classes, for example, with CycleGAN, we will need to add some tricks, add some extra losses that will allow us for this translation to happen. Something like this wouldn't really work, just encode and decode. We need some special tricks. Okay, so kind of like a related research area in this field is the so-called field of natural language processing, or dealing with language models. And the idea is that we would like to basically just understand human language and either understand or be able to generate it. And maybe if we are able to generate it, the model already has to have some understanding. So kind of these two things are kind of linked. The very early methods in these fields used some relatively rigid rule-based syntax trees. So like whatever the sentence I'm saying now, you would take it and then separate the different like positions of the words, what they mean, which word is linked with which, what is the structure of the whole sentence, and then try to use these rules to kind of describe the whole language. And that would be useful for some early models, but it's basically impossible to use for kind of like the super complicated and liquid language that we have now. And so later methods, especially with deep learning becoming more of a topic, these methods started to learn from data. So learn the rules about language from data. Right. So the recent trends with these language models are about using very large models and very large datasets. So just to put things slightly in perspective, there is this really big model called ResNet 152, which is already like really huge. It's almost impossible to use on your own PC. You would use some smaller versions of this, for example, in your own projects, because 152 version is too big, and that has about 60 million parameters, while the text generative models, namely the GPT-2, has 1.5 billion, and then the GPT-3 175 billion. So just so much more parameters, and the parameters are kind of the memory of the model, the storage where it can kind of like include all of the knowledge that it's being shown during the training process. And to kind of balance that, they also use very large training data sets. So while ImageNet is a famous image dataset, it contains like 1.2 million images. The model that we will be talking about today, CLIP, has been trained on like 400 million images or image to text pairs. So, and this scales even more insanely for the other models, right? So this is just to kind of like introduce this concept, and how they how this is kind of being described in these papers is that this is a natural language supervision. So we are training these models by the data contained in natural language, which is a bit kind of confusing description, because what they mean is actually by training on data from the internet, because like kind of naturally you would like to know, so where does all of this data come from? We have so many like millions of images and text pairs. What does this mean? Where can we actually get this data? So the answer is that we can scrape it on the internet, which has some problems with it, which we will see in the later slides of this class. But I think the naming that they call it, like the natural language supervision, is slightly iffy. Okay, so what's the deal with this? That these datasets are kind of beyond being collectible by a mere mortal. So basically me trying to scrape some websites, it would be like this amount of data is almost impossible to collect for me. I would have to have like, yeah, lots of resources, and this is usually the case of some big companies that can do this. And these datasets are then really beyond kind of any manual curation. So you cannot like look at every one of those data samples and then say, okay, these are correct, everything checks out fine, because yeah, it's just too much. So yeah, there will be some noise, and there might also be some other problematic data samples. And also these models are really beyond like being able to beyond trainable on usual machines. So even if we kind of just rent out a Colab instance somewhere, or not rent out, connect to it, we wouldn't be able to train these models, because they would just explode in the machine. It's too big for those. So right, let's talk about kind of how to use these language models. So it was kind of interesting to find that if we have a model that is able to generate sentences, we can kind of eventually get it to do some tasks for us. So for example, if we can ask it a question, we can almost like have it predict whatever the answer for that question is. And so in this case, sometimes this would have to be sort of slightly fine-tuned on this particular type of task. But instead of just putting some text input, you would put this text input as the question. To which category does this text belong? Is it this or is it that? And then the text. And then if you fine-tune the model, you could kind of have it predict the classes. So, which is kind of interesting, because that's sort of like doing almost like classification, but it's actually not doing the same thing. So yeah, it's kind of trying to excavate from this language model some knowledge about what it learned. And the last kind of background concept that we will need to talk about is how to combine these language models with vision models. And in order to do that, we will introduce the main model that we will be talking about today, which is the CLIP model. Right. So in a lot of these in a lot of the models we talked about in previous classes, you had some sort of like simple training task, and then you were able to later use this model that was trained on this simple task to do some other useful things. So this will be the case as well here. So we have a very simple task actually to train this model on, and then we will be able to use this for some other follow-up tasks. So this is not even relevant to this case, but kind of it's a similar task that we could actually ask image models to do. So if we have two images, like two images like these two apples, we want to kind of get a distance metric or something like an answer. How close are these? And I mean, is it the same kind of thing? Is it both apples? We as humans know that these are both apples, but we also know that, hey, one of them is red, one of them is yellow. There is either some difference in like the type of the apple, or maybe some other kind of like, maybe one of them is not ripe enough yet. So there is some distance. And then what if we compare like these two and then the other two samples? So like, okay, I mean, surely the two apples should be sort of closer together than when you're comparing like an apple and a banana. And it's sort of like, for us, it makes sense quite clearly, but for the model, it might be quite hard. Like, this also has a yellow color as this, right? But maybe what matters in these cases is not the color, but maybe shape, or maybe kind of like the belongingness in some categorical tree. Right. So in this task, for what we want to do in this class, so kind of going from text to images, we want to do this other simple proxy task. And that is to do exactly something like this, except with pairs of image and text. So given a short text, like a picture of a banana, and given a sample image, we want to have this model, whatever this model is, we don't really care about that, but like, let's have this model that will output us a distance kind of, or similarity metric. So if they are very similar, it will give, we want it to give us very high score. If it's not really similar, for example, if the sentence is saying a picture of an apple, comparing with a banana, then we would like to have the model kind of give us low score, saying, hey, okay, this is nonsense. Or other way around, if this is a, yeah, I mean, this is also a mismatch, but like one of the text is the same as here, but they are again not the same two items. So we would like to have this as a low score, right? So imagine, okay, I mean, this is kind of a very simple proxy task. Imagine what we could do with this. So if we had this model and we have some sample image, like an image of a banana, and we kind of don't know what it is, so we would like to use this model to get the class. We could use a list of sentences. We would have to generate these sentences. So it's kind of not super sure or not super clear how we would get all of these sentences, but we would have to kind of guess different sentences and try out all of them. So one of them would be a picture of a banana. Another would be a picture of an apple. And so basically you could have like a picture of fill in blank, and then try different items in that blank, and then use this model to kind of give us the best, to give us answers. And so the largest similarity between these two will likely hint that this item is actually the thing that we have in that one field. So this is called zero-shot classification, because if we had this model which was trained somewhere, magically occurred from the space and fall into our hands, and we can just use it, we don't really have to kind of show it any new samples or any new labels. We just can use it as a zero-shot classifier. So I mean, like, you can imagine that we are getting to the point where we will say that, okay, actually we do have that model. And so how this model could be used is, for example, look at this, or show it this image, and then check the different sentences, and basically when it's firing on a photo of guacamole, a type of food, then we say, okay, this is the label then, guacamole. Right. The problem there, or like a question that you already might be thinking of, what if we ask it a wrong type of sentence or wrong type of label? Maybe what if this label is kind of not something that it ever saw? What if it's coming from other domains where this was never in the training dataset? Or yeah, there might be other problems. Also, we cannot really spend infinite amount of time, and we cannot really like generate all possible sentences and just check across everything. We have to somehow select these. So the generation process of these sentences also is a bit iffy. So yeah, let's see. Well, actually, we do have this kind of model, and it is called CLIP. It is called Contrastive Language Image Pre-training. And it has been released basically last year, basically 1 year ago, 1 year and a bit ago, by OpenAI. So the data that this model was trained on has been scraped from the internet. So they somehow do describe a little bit about how this data is collected, but not in super great detail. And it is containing 500 million pairs of images and text snippets. So given like a website, basically you would download all the text from that website and all the images. And maybe you could do some sort of like proximity, like this image was here, and then there was some title either on the image itself or like nearby it, or maybe the article is talking about something. So you have kind of like ways how to generate pairs which say this image corresponds to this text. And remember, as we talked before, this is very unlikely to be hand-checked by people because it's just too many. So we have to have, well, they had to have some sort of mechanism how to do this automatically. Okay, well, so this is for the data. For the model, they used existing architectures. So yeah, they are not trying to reinvent the wheel. We already know that when working with images, we have all sorts of convolutional neural networks which work very well with images. So something like ResNet 50 or other models. And for text also, from other research, kind of newer one, there are some transformer models. And so they used these to make a bigger architecture. So yeah, let's look at this then. This is more or less the schema of the model. So we have the clip model here. This is this box that we were kind of like thinking about previously as well. There is a language encoder, which would be like a model which is known to work well with text and language, and that would be fed with some input text and output something. And then a vision encoder, which would be using some model which is capable of working with images, so the ResNet 50 or other models. And that would be fed with a input image. So there would be some sort of mechanism. We will not go into too much detail about like the exact way how this is implemented, but a thing that will then eventually spit out a similarity metric. So when making the dataset, basically, if we have these two kind of samples that we know are linked together, so this is like the positive pair, a picture of a banana and then the banana photo, we know that these two should be correct. So this is the positive sample, and we would assign it with like a similarity metric 1 or some high number. Whereas if we have a negative pair, so a picture of a banana and then an incorrect image with this, we would assign this with a low similarity metric. And so something like this is called contrastive learning, where you are basically, you have pairs of samples and you want the ones that correspond together to be kind of pushed closer with each other, and the ones which are not the same to be pushed away from each other. And yeah, there's some kind of more complication in this point, the way how this is being trained. They are also not just predicting one by one or like training it with one by one sample, but at every time the training occurs, they are working with a whole batch of samples. So a whole sample or a whole list of samples, and some of them are positive, some of them are negative, and the ratio of how many positives versus how many negatives actually matters as well for the training. It's beyond this, I think. So just know that it's kind of slightly more complicated. Right. So we have now talked about this model clip, which is this model that is capable of giving us a distance metric or a similarity metric for two items. If they are the same thing, even though one of them is image and one of them is text, it will give us high similarity score. If it's not, it will give us low similarity score. How on earth would we want to use this for image generation? Okay, well, you might already kind of like know from the previous class that it will likely be by framing the loss function of this thing that we want to now do in kind of some smart way. So this is work coming from the sort of AI art community actually, where this model clip has been released and then people were experimenting with it, and so these two have released some versions of this notebook that is kind of doing the initial versions of this what we will talk about now. So how to use the clip as a sort of loss function, and how to even actually like do what we want to do with it. So given some text input, a picture of a banana, and already existing pre-trained model that we download from OpenAI and don't touch anymore, how can we achieve creation of an image which would actually correspond with this thing, with this description? Because that's what we want, right? To go from a text to some generated image. Well, so this is the task. For this text input, we want this thing to create an image which would have a very high similarity metric. So basically, change this image so that this model, when used as a loss, will give us very high similarity metric. And so in that moment, we could just try with every possible image on the whole planet, just try randomly sampling all possible all possibilities and just stop at the one that is the highest, or we could have some smarter ways. This whole technique is actually inspired by a deep dream technique, which you might have already heard about. I think in the class you might have already coded something similar, actually. So let's see. This works a little bit similarly, and let's now talk about deep dream. So for some input image like this, and some existing model, like in the previous case, right? A frozen pre-trained model that we don't touch. For deep dream, we select some neuron, and basically the task here becomes to change this original input image so that this neuron that we selected is firing as much as possible. And for example, if this neuron was kind of firing on spherical patterns in the original image, over iterations of the deep dream algorithm, we will kind of get more and more of these circular patterns in the original image, because they satisfy this one selected neuron. So after many iterations, we probably this is some neuron selected that likes dogs, and so it is kind of just generating some sort of dog-like patterns in this. Right, and it is kind of we are kind of almost training the original image so that it becomes in some way without touching the model. So this is the technique that is kind of something that we will use for this text-to-image task as well, because the situation is quite similar. We have a given model which knows something, and we have some prompt that we want to kind of maximize in some way, and we want to get the best possible image for that prompt. So, right, we in both of these cases, we could just throw randomly infinite number of images, and one of them then would be the best one, actually. It's like the monkeys and an infinite time and them writing a book, right? One of them will hit and write the absolute epic, but we don't have to do that. And also, we don't have infinite time and space. So there is a smarter way, and this way is actually very similar to how training works. Given what we specify as the task, we can kind of propagate the direction in which the original input image should change so that we minimize or optimize whatever we selected to do. And so this is same as when training a neural network, where we are kind of back propagating these directions, which are called gradients, and they are usually applied to layer by layer of the model, going from back to forward, which is called back propagation. And then we edit these weights a little bit so that they kind of minimize whatever the loss was. So this is similar, but we don't really touch the model. We back propagate all of these gradients all the way through the network, and then get all the way to the image. And even and that's the thing that we will change, not the model, but the image. And so that there we get some sort of directions that we know that we should change this image in. So yeah, let's kind of visualize this now. So given some sort of input text, which is a picture of a banana, and given some, let's say, random image or maybe a noise at the beginning as well, we want this similarity metric of a pre-trained model, pre-trained clip, to be as large as possible. So this is the similarity that we want to maximize for this particular pair. So we will back propagate all of these directions through this vision encoder all the way to here, and then this image will basically get all of these arrows which are telling for the RGB values of this pixel, change this in this way so that the image becomes more banana-like, or whatever the text prompt that we chose. So this is one scenario where we plug in the image directly to this clip model. Another scenario, which is maybe more common sometimes, is that we don't actually just optimize the image, but we have some model which is creating these images. So we would basically go beyond that. Let's say it's a generator network, and so we would propagate these directions all the way to like the latent vector, the code that is generating this image. And so this is sometimes this is an easier task because let's say this vector has like 1000 numbers, 1024 numbers, whereas the image would actually have super large resolution. So it would be really hard to optimize the image, but actually it is quite easy to optimize this latent vector, this smaller representation. And so we are kind of back propagating the directions in which we should move for this latent vector, so that when we change this image will satisfy this model in a way that the similarity score goes up for this text input. So yeah, let's actually see this in action a little bit. So this was the example that we saw at the beginning in the motivation section. We have a face and we wanted to like change it in a direction of a vampire. And so we start with some image here. We have this text prompt, and we have the task of maximizing whatever is coming out of the clip by changing this latent vector. And so iteratively, we will change this latent vector a little bit by little bit. And so basically, that's exactly what we see here. These frames of this video are the individual iterations of how this face is slowly morphing in the direction of something that satisfies this model as a vampire image. All right. So, yeah, I guess let's talk about slight complications with this whole scenario, because until now it all seems very useful and functional and everything is kind of all right. But let's talk about this model. So it's a sort of assembly of a bunch of other things. If you kind of remember that this clip model, I mean, these two encoders, they are different architectures. This is like a transformer for texts, and this is a ResNet for images. But they are trained from like the dataset that the clip, the authors of clip collected for it. So that's kind of one source of data. And so these two kind of should be linked together more or less. Then this generative model that we have here probably comes from some other direction. So we probably can give it our own model, or like the model generating faces, for example. And so it's kind of a modular system where we are matching together some different types of models. And yeah, there are some concepts with this. So this the selection of these networks, if you kind of know a little bit about the different notebooks that you can use for text to image generation, or actually later in this class when we will be playing around with this notebook, you will be able to notice that it is like a selection of different models that we can use. So that's kind of like selection for these different boxes, what we will place there, what we will use, like which model, and that will influence like the speed, but also kind of the performance. So right, what happens? We have three models, right? We have a text encoder, an image encoder, and then a image generator here. How do these three models interact? There are kind of two interesting moments. One is that what if we are asking by giving the prompt, the text sentence, something weird from a model which is able to generate images of, let's say, just faces. So what if you ask not, hey, I want a face of a vampire, but what if you ask, like, I want a tomato? Will this clip model, will it be able to kind of convince this generative model to generate a image of a tomato? Probably not. It will probably still be somewhere in the domain of faces, because that's the only thing that this model knows. The image generative model knows, but it will try to push it all the way there. So it's probably going to be like maybe slightly red if it's tomato. And because sometimes these models are being trained with a lot of like random augmentations, it might actually look quite like weird as well. So, but yeah, but we cannot make it kind of go beyond its own domain of data too much. What happens if one of these models, one of these three kind of components in this whole scheme, what if this model was biased? Or what if it was trained on some biased dataset? Well, the thing is that the bias will propagate throughout this whole system. So even if our kind of generative model is let's say, clean, then if this clip model is biased, it will kind of pollute with bias of this model the other components of this. And that actually will be a bit of a problem, as we will see. All right, so now it's quite good time to have a pause. And then after this pause, we will talk about the bias in these large language/vision models.